Hey everybody, Dr. Retzek back with you. This is our second video for Honors Calc 4, and it's all about the introduction to section 14.1. All right, let's get started. So this is section 14.1, and it's all about functions, which sounds like a funny title for a section because you've been working with functions this whole time, all through calc, and even before that. And yet here we are in 14.1 talking about functions. So let's remember what a function really is from the olden days, and then we'll see the new types of functions that we're going to be looking at here in chapter 14. So in the olden days, functions you thought of probably as graphs that happened maybe in the xy plane. And so you had some curve, and that was the graph of a function, y equals f of x, and maybe all the actions happening between a and b. And you ask all sorts of questions in calc about functions like that, like what's the slope at each point, or what's the area under the curve. And we're really good at that for functions that look like this. And what we want to do is translate those capabilities into more complicated settings. So this is an example of a function. The function maps the interval AB to the real numbers, meaning you plug in anything you want between A and B, those are the inputs, and it will spit out something that's a real number. Those are the outputs. Domain and range are the words. Okay, great. What we're trying to do here in Calc 4 is we're trying to extend all the stuff that we learned in Calcs 1, 2, and 3 into situations where functions depend on more than one variable. So the questions we ask will be directly analogous, but the techniques are going to be harder. And here in 14.1, they're just trying to get us to start thinking about this idea in more than one variable. So the big goal is to extend Calcs 1, 2, and 3 to functions of several variables. That's what we're trying to achieve this quarter. And so the first thing we got to do is we got to think about, well, what's the picture now? And the pictures, they play a huge role in trying to reach our goal. Now, instead of the inputs being the x-axis, one variable, and the outputs being on the y-axis, one variable, now the inputs come from the xy plane, and the outputs are measured on the z-axis. So outputs are still numbers, but inputs are now ordered pairs. The result is you're no longer looking at a curve floating above the x-axis, but rather a surface, like a flying carpet, floating above the xy plane. So that's the x-axis coming out of the board towards you, y-axis going to the right, z-axis is up. It's no longer y equals f of x, now it's z equals f of xy. So you got this flying carpet. The graph is now a two-dimensional surface floating above the two-dimensional xy plane. And each spot, x comma y, flat down here in the xy plane, corresponds to some value on that flying magic carpet. Okay, so that's the leap. Think of all the questions you could possibly ask now in this new setting. Like, check out this drawing. What if we had a flying carpet kind of like this? Where we have kind of a mountaintop up in this area up here. And then we have this giant crater down in this area down here. Depending on where you were on this surface, so imagine this is still floating somewhere in three-dimensional space. So maybe the axes go like this. X, Y, Z. Depending on where you were on that surface, you would detect totally different things. Like a person standing right here would feel like, oh, flat, I like it. Or a person sitting down here would think, oh yeah, flat, I'm in the bottom of some canyon. But a person right here, maybe these guys are on the side of Bishop Peak right here going for a hike, they might think, oh man, super steep. So depending on where you are on the surface, you have all sorts of different data about what the surface looks like. Notice also that the person at the mountaintop and the person at the bottom of the valley, they would say they were at a max or a min, and somehow maxes and mins correspond to spots where, well, back in the old days, maxes and mins corresponded to spots where the slope was 0. Now it's not so much the slope as it is kind of a tangent plane. So if you make a plane tangent at a max or a min, that plane would be horizontal. So maybe we can find maxes and mins by figuring out where tangent planes are horizontal. And there's all this analogy building with Calc 1 where we're going to try to take those techniques and extend them to this new setting. Okay. There is some terminology that you'll encounter here in section 14.1. And the one I really want to talk about right now is what's called a level curve. So a level curve is a curve that lies in the XY plane and corresponds to inputs that put you at constant output values. So imagine this curve on our hike on Bishop Peak right here. On the surface, that curve of red points is at constant z value. So maybe that curve right there is all at height z equals c. You could ask, all right, well, what values down in the xy plane produced all those outputs with value c? So you're imagining projecting straight down into the xy plane, and you're thinking about all the xy's that when you plugged them in, put you perfectly at height z equals c. That curve down there, that's called a level curve. Topographical maps, when you're planning a big hike, topographical maps show you all the different level curves, sort of all superimposed. And you might say this is f of xy comes out to c. So this would be some expression with x's and y's in it. And whatever the function is that produced that surface, that function equals c is the curve down in the xy plane that makes outputs with constant value c. Now, if you change what c is, then you will get a totally different level curve. So imagine we went down by this guy now and projected straight down. Well, maybe these are the points that put you at that constant value. So it really depends on C what the level curve is down flat in the xy plane. So basically that's all that's happening here in 14.1. Rather than thinking of curves y equals f of x, we're going to think of surfaces z equals f of xy, or even hypersurfaces in four-dimensional space, w equals f of xyz. If it was w equals f of xyz, it wouldn't be level curves anymore, but level surfaces. There would be complete collections of points, xyz, that made w come out to a fixed value. But I'm sure you don't blame me for not trying to draw that, because it's hard to think of the domain as being all of 3D space, x, y, z, and then there being some fourth variable where you're going to measure the outputs. Hard to draw, but not much of a stretch as far as maintaining the analogy. So that's it. Start reading in section 14.1, try some of those suggested problems for the night, and come to class with questions. We're just trying to think of functions now as depending on several variables. All right, go to it. I'll talk to you next time. Bye.